Hi. In the previous video, we reviewed atoms and where subatomic particles, I try to combine those two words, where they exist in an atom. So protons and neutrons are in the nucleus and our electrons are in the electron cloud. And just to cover the possibility of using any charges or any of these atomic number or mass number or charges, you will probably see charges here and there. But to review what these mean, our atomic number is this number that's at the bottom. And for the most part, this is usually omitted because this number corresponds to the identity of an atom. So a helium is not a helium if it doesn't have two protons, right? The atomic number of helium is always going to be 2. So it's kind of redundant in a way. But another example here, magnesium, we have 12 protons. That means it's magnesium. If that changes, it's no longer magnesium. And then you have above here the mass number. It's sometimes abbreviated as A. The atomic number is sometimes abbreviated as Z. The mass number is the mass of protons and neutrons, which are in the nucleus. Those are the only ones that contain mass that is not negligible. The electrons are negligible in terms of mass. So you'll see these types of symbols whenever there are isotopes. So for example, carbon, which is the star of this entire class, has 3 isotopes, which is C12, C13, C14, and what's differing between these is that they have different amounts of neutrons. Remember, the number of protons never changes. If not, it's not carbon. So where do our electrons live? We reviewed that they are outside of the nucleus in this cloud that we call the electron cloud. Now, that cloud actually has a scientific name. So those are orbitals. And if you remember, hopefully, from Chem 1, Chem 2, mostly Chem 1, then you know that there are different types of orbitals. And depending on what number of electrons there are for an element and how big that atom is, this will fill different types of orbitals at a time and different energy levels of these same orbitals. So we have 4 different kinds: S, P, D. There's more, F, but that one gets kind of really complicated. P's we like to think of as like a dumbbell shape, and then D orbitals are typically like 2 dumbbells kind of stacked on each other. And an S orbital is a sphere, so S sphere. So we will look at these orbitals in action. Once we pull up this simulation, you can click on it using this link in your slides. If you successfully pulled up this website, you will see that we have different orbitals being displayed here. Specifically here we have the shape of an S orbital. And for some reason it wasn't loaded already, but if it's not loaded, just like I just did right now, just click on S orbitals. And this is showing the X, Y, and Z plane. So these are the 3 dimensions, the 3 dimensions that we live in this world, right? And this is showing you how it's a sphere all around. It doesn't change. If you change it on a different axis, it's always going to be a circle, a sphere specifically, not a circle. We draw it like a circle. Then we have the p orbitals, and these are more like a dumbbell shape. Now in textbooks they kind of draw them more or closer to what we think of as a dumbbell. However, in reality they are more like these bigger bubbles. So this right here is showing you the actual probability distribution of electrons, where it's kind of, you'll always find electrons in these relative areas, right? So that's why these are shaped like this. And there's 3 different p orbitals. You can go ahead and explore those. Now notice that this is 2p orbitals and these are 3p orbitals, so these are an energy level above those, so now they're bigger. So as you keep going from 2 to 3p, that's an energy level increase. We can go to 3d orbitals, which are, remember, a different shape. And remember, these are like 2 dumbbells shaped over each other. And the reason I'm bringing up all of these orbitals, these will be important for certain chapters, and I will discuss those then. So like I mentioned in the simulation just now, as you keep going up in energy, there are going to be different shells of orbitals. However, you can have the same type of orbital in bigger, higher energy levels. So you can have 1s and then 2s, 2p, 3s. So you learned about these in Chem 1, but I understand it can get kind of fuzzy. So what is the order of these? How do we know how these even fill? What is going on? How many does each of them fill? So depending on how many of each orbital you have in that particular set of orbitals. So s orbitals always have only 2 electrons, right? The first shell only holds a maximum of 2. Second shell, because it has both an s-type orbital and a p-type orbital, which consists of 3 different ones, we are going to have a total of 8. And as you keep going, as you are able to access different types of orbitals, D and F, you're going to have more access to more more electrons, right? So as you go down the periodic table, you're filling more and more orbitals. You have more protons, you need about the same number of electrons to balance those charges out, so you're going to need more electrons, and those are going to fill more orbitals. So electrons are represented by the up and down, and there are some, what I think of kind of sometimes as like glitches. So the energy level of the 4s orbital is actually in between 3p and 3d. You would think that we finish up filling all the 3s and then we move on to 4. It's not like that, right? That's not how things are in science, unfortunately. So how do these electrons fill? What is the order of all these numbers and letters, right? So lowest energy always fills up first, which makes sense, right? You want to fill up what you can as we go. But like I mentioned, there are some, they're called exceptions, but you can think of them as like discrepancies that we have noticed experimentally, right? But the idea of filling in the lowest energy first is called the Aufbau principle. So that's rule number 1. Like I mentioned, there are some exceptions. So this map right here, some people call it a Christmas tree, you can call it a pine tree, whatever you want. It is showing you the order. So we're filling in the 1s, we're filling in the 2s, then 2p, then 3s, then the 3p, then the 4s. See how this is coming in before the 3d. So there's exceptions to that rule. But the second rule that you need to know is the Pauli exclusion principle, where each orbital will always have a spin up and a spin down, right? They have opposite spins. Are they necessarily spinning in a circle like that? That is more physics, but you can know that there is just always one up and one down. And then finally, rule number 3 is Hund's rule, where if you have 2 or more empty orbitals of equal energy, one electron will fill until everything is half full, and then you start pairing everything. So orbitals, if you have like a set of them, let's say a set of the 3p orbitals, right? There's 1, 2, 3 orbitals. They want to be half filled versus having like some unpaired electrons. They would be rather half full. That is better for them. So here are some examples of what we were discussing. So let's start with hydrogen. The atomic number of hydrogen is 1, meaning it has 1 proton, meaning that if it's neutral, we are going to have 1 electron. It only has 1 electron, so the only orbitals it's going to access is 1s. Next up, we have carbon. It is atomic number 6, and that means it has 6 electrons. Remember, this order right here, 1s lowest to highest, is following that little pine tree. So we are starting here. It's always going to be in this order, right? 1s, 2s, 2p, 1s, 2s, 2p. Okay. So the 1s fills first, 2s fills next. You have 2 electrons left after that. They are going to remember Hund's rule. They want to be as close as possible to being half filled compared to pairing them up right away. So instead of having a 1, there I go. Instead of having an up, you are going to have an up. Instead of having an up and a down, I'm getting ahead of myself, you are going to have up and up, right? So that's Hund's rule in action right there. And let's look at a bigger element, phosphorus. This has 15 for the atomic number, meaning it's going to have 15 electrons. Fills up. Okay, we know the drill, right? It's going to fill up lowest energy to highest. And then by the time you get to 3p, you're going to see that there are 3 electrons left. And remember, they are going to half fill versus pairing up. So instead of having, the pair right here and then 1 left over, they're going to each take their own little room. Electrons are like antisocial. They want their own little orbitals.